This video is going to talk about the randomized block design and show you how to analyze it in R. Okay, so when we're running experiments, there's something that we're manipulating. It's the treatment, if you will. So that's the main independent variable is going to be the thing that we're manipulating. So if you think about the new food case, in new food we were manipulating the advertising level. We also manipulated the price and the location in the store. So we're trying to understand how that independent variable affects some dependent variables. So let's think back to new food. We had sales as the dependent variable. Now often there will be other um, factors that will affect the dependent variable. So these other factors are sometimes called nuisance factors because they're related to the dependent variable, but we're not necessarily manipulating them. So let's think back to new food. With new food, the store size definitely affected our sales. So if we put our product in a very high volume store, we sell more than if we put it in a low volume store. Okay, so store volume is a factor that's going to affect the dependent variable. So whenever you have other factors, these nuisance factors that affect the dependent variable, a good strategy is to block over them. Okay, so what do we mean by blocking over them? By blocking over them, what we mean is we're going to assign all of our experimental units. In the case of new food, those were stores, or I guess cities, in that we had a nested design there. So we're going to take all of our experimental units and put them into these blocks. Blocks are like segments or strata, so that those stores or the cities are similar. Now, if you think back to new food, we had two cities that mostly had larger stores and two cities that mostly had smaller stores. Then what we're going to do is we're going to assign the treatments randomly within the block. So within our two high volume store cities, we're going to put one in the low advertising condition and the other one in the high volume, high advertising condition. Likewise, in the two cities that had the smaller stores, we're going to put one in high advertising, one in low. Now, the reason we do this is because it will help us rule out that nuisance factor. So we didn't do that in the case of new food, and we saw the problems that we ran into. So had we thought of that beforehand, we would have been better off. So there's an old saying, you want to randomize, you want to block what you can. So block all the variation that affects the dependent variable that you know about, like store size, and then randomize everything that you can't. Let's look at another example now, and we'll do this one in R. So a lot of restaurant chains have audits of their franchisees. So you can think about a McDonald's or a Burger King. They have a lot of owner-owned franchisee locations. So some person buys a franchisee license and then opens up a McDonald's in a certain place. But the overall McDonald's brand wants to keep track of that franchisee and how that person is doing, because they have a reputation to maintain. So they employ evaluators who go out to the restaurants and see how the service is or how the food quality is. So let's say that a restaurant chain, could be McDonald's, has four restaurants locations A, B, C, and D, and they want to see how these are doing on service satisfaction. So how good is their service? Now, let's say McDonald's employs 6 different raters. Now, the rater is going to be one of these potential nuisance factors in that some raters are going to be more generous than others. And so if some raters are more generous than others, it would be a really bad idea to have only one rater rating a restaurant, because then a positive rater we wouldn't be able to tell the difference between a positive rater and a good restaurant. All right, so here's the data. It's in a data set called rest.csv, available from the Google Apps site. I've issued a couple commands here that I'm not going to type during the video, but let me just talk you through them. We're going to cast rater as a factor. Now what that's going to do is that it's going to tell R that this is a categorical variable, and therefore we need to make dummies for it when we throw it into a linear model. Likewise, I'm going to cast rest, the rest variable in this, as a factor, also requiring dummies. And I'm going to assign that letters, so we get the A, B, C, D. This is one way. Letters is a constant in R, if you want to see what that is. It's a constant, letters is a constant array, so letters 1 would be A, letters 2 would be B, and so forth. You can plot it and get your usual scatter plot matrix, or you can create an interaction plot. So let me show you that interaction plot. So in this interaction plot, I've got the raters plotted across the bottom, and I've got the restaurants plotted as different line styles / colors. So we can inspect this and see, for example, that restaurant C seems to be the best in terms of having the highest scores, and restaurant B seems to be the worst. A and D are kind of in the middle. Now it's also somewhat useful to flip this around. So let's look at rest, and we'll put rater on the other axis. And so what you're going to see in this plot is that clearly there is a rater effect, or it seems to be a rater effect, in that rater number 1 systematically gives lower scores than any of the other raters, whereas rater 6 looks like is a little bit more generous with the scores most of the time, although he doesn't like restaurant B for some reason. So certainly that solid line, red line 6 is a bit more generous. It looks like the dotted blue rater number 4 is a little bit more generous. So this is suggesting we better account for this in our linear model. So we're going to take out that rater effect. So how do we do this? Well, we're going to build a model, and we're going to have Yij being the measure of the dependent variable, in this case the score for that restaurant. So this is going to be the score for restaurant I given by rater J, or block J. Now we're going to decompose these scores into different components. We're going to have an overall mean. This would be the overall average satisfaction across our restaurants. Think of it that way. And then we're going to have a restaurant effect. So if all the restaurants have the same score, then all these alphas would be 0. Whereas if some stores or restaurants are better than others, the alphas will vary. Beta is going to be our block effect, or rater effect in this case, and we have some normal errors. So let's go fit this. I've given you the code, but let's type it again. So fit is an LM, and we're going to have score is going to be a function of restaurant plus rater, and we're going to use the rest data set. And if we look at a summary of this, we get a model that has 5 plus 3 coefficients. So these 3, the restaurant B, C, and D, are these alphas. These 5 rater coefficients are the betas. Those describe the block effect. And then here's our overall intercept. So let's interpret the overall intercept for this parameterization of the model. So 70 is the average score of a restaurant A and rater 1, or I guess it's just call it the well, it's going to be the average for restaurant A rater 1. Now, if it's restaurant B, the score goes down by 10.83. So we can say that restaurant B is 10.83 worse than restaurant A. The fact that we have stars by this coefficient indicates that there's a significant difference between restaurant B and restaurant A. This positive 13 is saying that restaurant C is better than restaurant A. So it's better by restaurant A than by 13.5. Restaurant D is about 1.8 better than restaurant A, although we can't say this is significant. Notice the p-value is not significant. So we have no evidence to say that A and D have different service quality. Now these rater effects describe the effect of the raters. So that 10.75 means that rater 6 on the average gives a rating that's 10.75 points higher than rater 1. And that's consistent with what we saw here. 1 was the most conservative and 6 seemed to be the most generous. And we see that since all these rater effects are positive, that means every rater on the average gives a rating that's higher than rater 1. Now, there's another thing that we should do, now that we've interpreted those, we should do a drop 1 on this. So let's do drop 1 on fit, and let's get our F test. I forgot the equal sign there. If we look in the course packet, on the next page, it's going to break it out. Now, the first thing that we do is we test the overall significance, meaning there are no restaurant effects or rater effects. That p-value is up here. It's tiny, so we reject H0 and conclude that there's something going on. Now here's that drop 1. This line up here, the restaurant line, is going to test the null hypothesis that all of our treatment effects, in this case the restaurant alphas, are 0, meaning there are no differences across the restaurants. Well, since that's very highly significant, we conclude there are indeed differences for the restaurants. We can also test, are there differences across our raters? So if we tested, that the effects for rater 2 through 6 are all 0, then that would indicate that all raters on the average give the same, scores. We're not seeing that. So we can reject the null hypothesis. It's significant, but not highly significant, suggesting we do have a rater effect as well. Now, sometimes we want to do more detailed comparisons. So if we go back to our coefficients, this was telling us how does B differ from A? How does C differ from A? So C was 13.5 better than A. What if we wanted to compare, for example, B and C? How much better is C than B? Well, the answer would be about 24. So if we take 13.5 minus 10.8, we get 24 point something or other. So it appears that C is about 24 better than B. But is that significant? You can test that significance using a function called Tukey's HSD. So let's do Tukey. Got to capitalize it since it's a guy's name. HSD. Then we're going to cast the fit object as an ANOVA object, and we get all of these differences. So let's go back to what I was saying. How much different is B than C? If we took C minus B, we get a difference of 24, indicating that C is about 24 better than B. If we go back and make another interaction plot, let's go back to this interaction plot. That's what what we saw. So C is indeed a whole lot better than B. We could also ask, is C better than D? And so if you wanted to know, is C better than D, we would look right here, C and D. So if you take D minus C, you get a minus 11.67, indicating that C is better than D, which is exactly what we saw in our plot. So that's how we analyze a randomized block design. We simply add dummies for each of our blocks and each of our treatment effects, and then the model tells us the individual effects.